Welcome. Today, we're diving straight into the foundational physics of electric charges and fields. We are going to unlock the invisible forces that literally dictate the physical world around us. So, if you've ever wondered about the hidden mechanics behind everyday static electricity, you are in exactly the right place. Let's get into it. To start, I want you to picture a very familiar, everyday experience. You're sliding across your car seat, you go to grab the door handle, and zap, you get shocked. Or maybe you've heard that unmistakable crackle and seen those tiny little sparks when you're pulling off a synthetic sweater in dry weather. Why exactly does that happen?
Well, what you're experiencing in all those scenarios, and actually even in the massive lightning bolts we see illuminating the sky during a thunderstorm, are just common examples of static electricity. Now, the word static simply means anything that doesn't move or change with time. So we're talking about electric charges at rest. These charges accumulate mostly because we rub insulating surfaces together, and they just sit there until they can discharge through something like your body. Decoding exactly how these stationary charges behave is our main focus for today's explainer.
Here's our roadmap for the chapter. First, the spark of static. Second, rules of attraction. Third, conductors and insulators. Fourth, understanding Coulomb's law. And finally, the electric field.
Okay, let's dive into part 1, the spark of static, uncovering that invisible force.
The story of static electricity actually goes way, way back, all the way to around 600 BC in ancient Greece. A philosopher named Thales of Miletus noticed that when he rubbed amber with wool or a silk cloth, the amber would suddenly start attracting light objects, like little bits of straw. Fun fact, the word electricity is actually coined from electron, which is literally just the Greek word for amber. Fast forward to the 18th century, and American scientist Benjamin Franklin figured out how to label these invisible charges, officially naming them positive and negative. Then, in the 19th century, Michael Faraday took a massive leap by introducing the concept of the electric field.
Moving right along to Section 2, Rules of Attraction and how these charges interact.
Through those early experiments, scientists quickly realized there were two different kinds of electrification. This brings us to the polarity of charge, which is simply the property that differentiates those two kinds of charges. There are two golden rules here. Rule 1, like charges repel. So two positively charged glass rods are going to push away from each other. Rule 2, unlike charges attract. A positive glass rod and a negative plastic rod, they'll be drawn right together. But what happens if they actually touch? Well, bringing these oppositely charged bodies into contact neutralizes or nullifies their effect entirely. The charges essentially just cancel each other out.
Which leads us perfectly into Section 3, Conductors and Insulators, or moving versus trapped charges. Knowing how charges interact naturally makes you wonder what happens when they hit different materials, right? And this brilliantly illustrates why stuff around your house behaves the way it does. Conductors, like metals, human bodies, and the earth, allow electricity to pass through them super easily. Put a charge on a conductor, and boom, it instantly distributes over the entire surface. That's why a metal spoon held in your bare hand won't hold a static charge. The charge leaks right through your conducting body and into the ground. On the flip side, insulators, like glass, plastic, or wood, offer high resistance. If you put a charge on an insulator, it stays exactly where it's placed. It's completely trapped. And that is exactly why rubbing a plastic comb builds up that static charge we talked about earlier.
All right, Section 4, understanding Coulomb's law, getting into the mathematics of force.
I want to introduce you to Charles Augustin de Coulomb. What's really interesting about this guy is that up until his work, we were basically just making qualitative, everyday observations. For centuries, humanity saw these invisible pushes and pulls, but had no way to accurately measure them. Coulomb was the one who finally transitioned us into precise quantitative measurement by giving a concrete mathematical formula to these invisible forces.
Here is the absolute core of his breakthrough, Coulomb's law. In plain conversational terms, it basically says that the electrostatic force between two charged objects is directly proportional to the product of their charges and inversely proportional to the square of the distance between them. In other words, move them further apart, and that force chops off dramatically. Now, absolutely crucial point here. This law relies on treating charged bodies as tiny point charges. We can only really do this when the bodies are super small compared to the vast distance separating them, which lets us assume all the charge is concentrated at just a single point in space.
But let's be real, the world rarely just has two isolated charges hanging out in a perfect vacuum. What happens when you have 3, 4, or 50 charges all interacting at once? Coulomb's law by itself isn't quite enough. For that, we use the superposition principle.
This just means that to find the total force on any single charge, you calculate the individual forces from all the other charges one by one, and then add them all up. And because force is a vector, meaning it has both a magnitude and a specific direction, we add them up using standard vector addition. It's like a giant puzzle coming together.
Let's transition to our final, and honestly most profound concept, Section 5, the electric field, the fabric of electrostatics.
So the most important thing here is actually defining what an electric field is. An electric field is defined as the force that a negligibly small, unit positive charge would experience if you placed it at a specific point in space near a stationary charge. We call the stationary charge that's actually creating the field the source charge, and that tiny hypothetical charge we use to measure the field, that's the test charge. It is absolutely vital that the test charge is vanishingly small so it doesn't disturb the original source charge. The field exists everywhere around the source charge, mapping out exactly how much force would be felt at any given coordinate.
Now you might be thinking, why do we even need this field concept? Why not just use Coulomb's law directly? Well, we have to look at the physical significance here. Imagine a charge moves. Does a second charge a mile away instantly feel that movement? No way. The effect isn't instantaneous. The idea of the electric field elegantly solves this time delay problem. When a charge accelerates, it produces an electromagnetic wave that ripples outward at the exact speed of light, carrying the field changes with it to that second charge. This means electric fields are very real physical entities. They aren't just convenient mathematical tricks we use on paper. They have their own independent dynamics, and they literally transport energy through space.
Before we wrap everything up, let's just do a really quick walkthrough of the key physical quantities and symbols from this chapter. Think of it as a rapid-fire review. We've got the electric field, denoted by the vector E, electric flux, represented by the Greek letter phi, the dipole moment, which is a vector directed from negative to positive, marked as P, and finally, those charge densities, linear, surface, and volume, which help us calculate fields when charges are spread out over strings, flat sheets, or solid objects rather than just being single points.
As we conclude, I want to pose this incredible point to ponder straight from the text. We established early on that like charges heavily repel each other, right? So if that's the absolute truth, why do protons, which all carry positive charges, sit so tightly and compactly together inside an atom's wildly dense nucleus without violently flying apart? The answer actually hints at a completely different, fundamentally powerful rule called the strong force, but we'll save that fascinating mystery for a future physics explainer.
I'm going to leave you with this incredibly powerful quote from the chapter regarding these fields. They are regarded as physical entities, not merely mathematical constructs. They have an independent dynamics of their own. They can also transport energy. It's truly marvelous to realize that the simple, everyday crackle of a static shock from your winter sweater is governed by these vast, invisible, energy-transporting fields that completely surround us. Thanks for joining this explainer, and keep questioning the invisible forces around you.